So the instruction says find A inverse given that the matrix A is 2, 6, 1, 3. So remember, we need to use the formula. A inverse is equal to 1 over the determinant of A multiplied by the adjoint of A. So that means we need to find the determinant, and we need to find the adjoint. So I'm going to find the determinant. So the determinant of A is equal to A, D, take away B, C. And I'm going to label my ABCDs in the matrix. So this is A, B, C, and D. This one is interesting. So A is 2, and I'm multiplying that by D, which is 3. Then I'm going to subtract B, which is 6. And I'm multiplying that by C, which is 1. So 2 times 3 is 6, minus 6 times 1, which is 6. The determinant is 0. Stop. Pause. Take a reality check. When this happens, remember the type of matrix this is? When the determinant is equal to 0, that matrix is called a what? Better remember. Watch. This is a singular matrix. A singular matrix. If the matrix is singular, then the inverse does not exist. A inverse does not exist. So once it is that you work out the determinant of a matrix and you end up getting the determinant being 0, that means the inverse does not exist. That means that there's no inverse for it. Because if the determinant here is 0, 1 divided by 0 is undefined if you put that in your calculator. And if this is undefined, how are you going to multiply that scalar by this? It doesn't make sense. So when you're finding the inverse of a matrix, the first thing you want to do is to check whether or not the determinant is 0. If it is 0, then it does not exist. The inverse of that matrix does not exist. Simply put, if the matrix is a singular matrix, then the matrix does not have an inverse. The reverse is true. If the matrix is a non-singular matrix, then that matrix has an inverse. Let's look at an example of that one. So here it says to find B inverse, given that B is this matrix, -1, 2, 5, -4. So I'm going to follow my formula, but this time instead of A, I'm going to use B. So I'm going to say, okay, B inverse is equal to 1 over the determinant of B multiplied by the adjoint of B. So I need to step to the side and work out the determinant of B. So this is the side, and then I'm going to label my ABCs A, B, C, D, because I know the determinant formula. So the determinant of B is equal to AD minus BC, and A was -1 multiplied by D, which was -4, and I'm subtracting B, which is 2, and I'm multiplying that by C, which is 5. Then I'm going to work it all out. Negative times negative gives me a positive. 1 times 4 is 4. Something says subtract, so I'm going to put back the subtract. And then 2 times 5 is 10. So we have 4 take away 10. So we're going to end up with a -6. So the fact that it is not 0 means that the determinant is that means that the inverse exists. So that means we need to find the adjoint now. So the adjoint of B, ADJ of B, is going to be, you remember to find the adjoint? I think you might remember. So find the leading diagonal, and we're going to switch the elements. So -1 becomes -4, and -4 becomes -1. And then I'm going to keep my off diagonal elements, but put a negative, apply that negative to it. So a negative by a +2 gives me a -2, and a negative by a 5 gives me a -5. So this is the adjoint of B, and this is the determinant of B. I'm not done yet, because it says that to find B inverse, I need to multiply 1 over the determinant by the adjoint. So I'm going to do that now. So I'm just going to rewrite the formula so that I am guided by it. I don't make any mistakes. So it says 1 over the determinant. So that's 1 over, my determinant was -6. So I can factor out the negative there and put the 6 here, multiplied by the adjoint. And see, my adjoint is over here. So -4, -5, -2, -1. There you go. Does this remind you of scalar multiplication? Yes, it does. So we're going to take all of this, including its sign, and multiply it by each element, just like with the distributive property. So this will now become -1 over 6 multiplied by -4. And I'm going to do it with this as well. So it now becomes -6 again, or -1 over 6 multiplied by -2. And I'm going to take it and do the same thing with this element. So it becomes -1 over 6 multiplied by -5. And it is not complete until I do all the elements. So -1/6 by -1. -1/6 multiplied by -1. Remember? So now, because it's fractions and it's easier to work with fractions, I'm going to convert all my whole numbers here into fractions by doing this, dividing them by 1. So it becomes easier for me to work with. And then I can simply multiply them across. So negative times negative will give me a positive. So I know my answer should be positive in the row 1, column 1 element. 1 times 4 will give me 4. And then 6 times 1 will give me 6. Good. Let's do this one. Negative times negative will give me another positive. So I know my row 1, column 2 element is going to be positive. So 1 times 2 is 2. And 6 times 1 is 6. Let's look at this one. -1 times -5 will give us a positive 5. And then 6 times 1 will give us 6. -1 times -1 is a positive 1. And it's over 6 times 1, which is 6. If you notice, because the top part here is 1, I simply just put everything else over 1, over the 6, right? So it was on 4, put it over the 6. 5, put it over the 6. 2, put it over the 6. 1, put it over the 6. But more importantly, you had to watch for those negatives. So negative by negative end up with a positive. 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 And to clean it all up, we can simply just reduce where possible. So let's go now. I know that 2 can go into 4 and 2 can go into 6. So 24 goes 2 times and 26 goes 3 times. So in its reduced form, I'm going to have 2 over 3. 22 goes 1, 26 goes 3. In its reduced form, 2 over 6 becomes 1 over 3. There's no common factor between 5 and 6 other than 1. And 1 won't get us anywhere. So this still remains 5 over 6. And the same is true for 1 and 6. 1 over 6. So this is its reduced form. This is the inverse of B. So B inverse is this matrix here.